Welcome to the series of videos and looking at water testing to do with a module with the HSC chemistry course, and we're going to start off by looking at water testing and common ions. All water samples, well not all, but most water samples have ions in them, okay? You've probably gone to the store and bought water. Even in that water, spring water has lots of ions in it. Water from the tap has ions in it, okay? Deionized water, the one that you use to do your ironing with, because I know you do your ironing, that has the ions taken out, okay? And we use that water when we make up solutions in the lab. But if we start talking about common ions, what other ions are we talking about? So there's lots of them. So if you just think about sodium chloride, right, common salt. So we've got sodium and chloride ions. We've got magnesium ions. Whoops, 2+. We've got potassium ions, right? Potassium ions are very, very important, and same with sodium for nerve conduction. We've got calcium ions, sulfate ions. Okay, and there's many more, but they're common ions that you find in water bodies. So they're some of the common ions there. When we talk about water that's fit for drinking, we call it potable water. All right, potable water. And that must have a low ion concentration, okay? Otherwise it tastes salty, all right? So how can we test for water samples? Well, let me get another colour here and we'll see how this works. So I might do it over here actually. We'll start here. So tests for water samples. And we can say that they can be wet lab, right? Or they can be instrumental. Okay, so let's look at some qualitative tests. Well, that would be precipitation, right? So precipitation tests you're quite familiar with, and you've probably done the good old precipitation test for sulfate. So if we want to test for sulfate, then you would add what one? Barium. Good on you. So we'll test it with barium nitrate. Of course, you'd have to acidify the solution first to make sure that there is no carbonate present, because carbonate would precipitate with barium. So we acidify it, then we add barium nitrate, and if there's any sulfate present, then that will precipitate out as barium sulfate. Okay. We can also test for silver, right? Silver is a heavy metal ion that we don't want in our body because it's a bioaccumulant. It increases its concentration in our tissues, and we don't want any of what's called biomagnification occurring in the food chain. So that's something we need to test for. So if we were testing for silver, then we can add chlorine ion to that, and that'll precipitate out as a white precipitate, silver chloride. So we can use wet lab methods there. We could use, if they're metal ions, we could use flame tests as well, right? And that'll give us a colour, a characteristic colour. We could make that more quantitative with flame tests if we wanted to use a spectrometer, which will then give us specific emission spectra. But wet labs, precipitation is the way to go there. So when we talk about wet labs for quantitative, if we want to be more quantitative, we can do gravimetric analysis. So what we can do is we can add our barium, and then we could measure our barium sulfate gravimetrically and determine the amount of barium in the water sample. Same for silver, etc. And so we're going to be looking at some water tests in future videos, and we can see that gravimetric analysis is used to determine some features of water. If we wanted to do instrumental analysis, then we could do one, atomic absorption spectroscopy. Okay. So that's going to be very, very precise, measures minute, small concentrations, very specific to ions. Whereas gravimetric analysis will be not as specific, because yes, even though we're adding sulfate to precipitate barium sulfate out, we may have some other ions in there that would be in the precipitate, and if your experimental procedure is not very reliable, you might have some contaminants in there, etc. Whereas atomic absorption spectroscopy is more precise. It is specific for a particular metal ion. Okay, and then we can have instrumental analysis where we're using data loggers, so we can have ion selective electrodes, right? So we can measure concentrations of salts in water by using ion selective electrodes. They're portable, right? You can't carry around an atomic absorbing spectrometer with you, although today they're getting smaller and smaller. But you can take out conductivity probes, etc. Quick, easy, portable, and they can give you some great information. So that is a quick little example of how we can test for ions, common ions, what does potable water mean, and how we can do our tests. And let's do a quick question and see how we go. All right, on to a question now, looking at how we can measure a common ion in a water sample. And here in this particular example, we're going to be using gravimetric analysis by precipitation. So a 5 ml sample of river water was collected. Right, so here's our 5 ml sample, okay, to test for silver ions. After acidification, silver nitrate was added. All right, so we added some silver nitrate. All right, so let's look at how we do this. So we've got our silver ions that we've added, and we've got the chloride ions that are in the water sample that we want to determine. That forms the precipitate silver chloride. Now we're told that we had a mass of 0.235 grams of our silver chloride solution. Now with this equation here, what we can see is we've got our silver ions and our chloride ions. The chloride ions are in the water sample, the silver ions of what we've added in the silver nitrate, and we've got a precipitate here, and we've been given the mass. So let's see if we can calculate the concentration of chloride ions. First of all, let's do it with just the number of moles. Okay, so let's work out the number of moles that was in our precipitate. So that's its mass divided by its molecular mass. So the mass is 0.235 divided by the molecular mass of silver chloride, which happens to be 143.35. And so that works out to be 0.001639. Wonder if we can see this here, but we'll just keep going. All right, so that's the number of moles. Now, the molar ratio is 1 to 1 to 1. So the number of moles of silver chloride produced is equal to the number of moles of chloride in the water sample. So therefore, the number of moles of the chloride in the water sample is 0.001639. Now we want to make this into parts per million. So the thing with parts per million, we need to understand and remember it's milligrams per litre. So we've got to convert this into a mass. So we use our relationship here. All right, number of moles is equal to the mass over molecular mass. And so therefore, if I want to convert number of moles into mass, I've just got to times it by its molecular mass. Well, in this case, it's the relative atomic mass of chlorine. So the mass of chlorine is the number of moles times its relative atomic mass, right? I'll just put mm to keep it the same formula there, but remember it's relative atomic mass. The number of moles, 0.001639 times 35.45, and that turns out to be 0.058 grams. So now that's 0.58, so we've got 0.058 grams in, and what do we have? 5 mils. Oh, it should have been 5 litres. It's getting carried away there, so let's just fix that up. Okay, so it's 5 litres, right? So in 5 litres, remember we wanted milligrams per litre, so let's first of all change this to milligrams. So we've got to divide that by 1,000. Well, actually, yeah. We've got to times it by 1,000 for milligrams, right? So that's 1, 2, 3, so it's 58 milligrams in 5 litres. But then we've got to divide both sides by 5 to make it per litre. And that turns out to be 11.6 milligrams per litre, which is 11.6 parts per million. Okay, so we've done it that way. I'm going to rub this off in a second and show you another way to do it, and still get the same answer. All right, so give me a moment. I'll do some erasing. Be back in a tick. All right, let's have a look at another way. I worked out the number of moles here and used the molar ratio. Another way of doing it is, I guess, is a percentage composition. So in other words, we can say, well, out of our silver chloride, so the percentage of chloride in silver chloride is 35.45. So that is the chlorine there, right? And then the molecular mass here, which was 143.35. That'll give us a percentage. So if we do that, 35.45 divided by 143.35, right, that's going to say 0.2473%, right? If you times it by, it will be 100, it'll be 24.73. So we can get that and times that by the mass of the precipitate, which was 0.235, 0.058, right? And you can see that that there is the same as that there. Okay, so the mass of chloride, and this is the mass of chloride because we found out the percentage first, and then whatever percentage we had, we times it by the mass. So that's becoming the mass of chloride right there. So it's the same value, and then you just do the same calculations from there. So it depends on how your brain works. Okay. So that is how we test for water, common ions, and do a simple calculation to work out the concentration of a common ion in a water sample. See you in video 2, where we look a little bit more at water testing.